Okay, thank you for those of you coming here for the first in a series of 5 talks, a virtual computer architecture seminar. Today, we're very pleased to have Chris Fletcher. First, a few logistics. If you're not Chris or right now me, please mute. This talk is being recorded, so if he answers your question, some of what you said might be revealed. We're going to save questions until a couple of breakpoints into the end, and then submit your questions by chat because it's just too hard to arbitrate the voice questions. All right, so Chris is an assistant professor at in computer science at the University of Illinois at Urbana-Champaign. They're a Big Ten school who we're not playing football with this year. He has broad interests ranging from computer architecture to security to high performance computing, NSF Career Award, Google Faculty Award. I guess I forgot to say who I am. I am Mark Hill. I'm a professor emeritus at the University of Wisconsin. Let me finish with, many professors are accused of being oblivious about many things. But Chris is one of the few who chose to use oblivious as the first word of the title of his award-winning MIT PhD thesis, Oblivious RAM from Theory to Practice. Without further ado, Chris.
Thanks a lot, Mark. And yeah, with respect to people's information being revealed in the chat box, if you decide to make a question, there was all sorts of side channel related jokes that will become apparent as the talk goes on. So thanks very much, Mark. My name is Chris, and the talk today will be on principled secure processor design. So let me try to transition slide. Okay, great. So just before I begin, a big shout out to my students and collaborators, without which this work would have definitely not been possible. Try to transition again. My keyboard work. Good. Okay, so the question that I'm going to be using to kind of jumpstart this talk is, how good is process isolation nowadays anyway? And so what I mean by that is, suppose I'm trying to outsource some computation on my sensitive data, and I'm trying to say use any of the modern facilities today available today for doing so, like the cloud. And let's just say that the cloud is an untrusted party, because we usually assume that that's the case, or that things can happen to our data when we throw it over the wall. So kind of the computing abstraction that we have in mind when we chuck our data over the wall to be computed upon is something like this slide. We have some private data, some secret data S, I'll color the secret data red. We're going to compute on it with some function or program P, and for the purposes of this talk, I'll just assume that the program P is public. And I'll get some secret result out of that computation R, which is secret because it depends on the input S. And the mental model for people for why they believe that their data should be kept private involves a combination of systems and cryptographic mechanisms. So for one, we kind of assume that cryptography, like encryption and decryption, is going to protect our data in transit. So we'll encrypt our data, we'll share a key with a remote piece of hardware like a processor. We'll send the encryption over to the cloud, which will get our secret data safely into the black box, which is the remote processor. We'll do the computation once the data is decrypted inside the processor, and then by the time the data leaves the processor, we'll re-encrypt it and get an encryption of the result back. So we assume that cryptography is kind of saving the day for data as it goes in and out. And when the data gets decrypted inside the box and computed upon, we rely on a number of systems mechanisms like virtual memory isolation to protect the computation as it's happening from, say, other processes that are running on the same machine. And so you put these mechanisms together and we get no unauthorized leakage of our input S. And so the problem with this view of the world is that in actuality, this black box that we drew, that I kind of just illustrated as an input-output function, is more complicated due to microarchitecture, which makes up the processor. So to give a simple example, processors today actually kind of look like the picture that I have on the right-hand side. You can kind of view a processor as this thing called a core, which runs instructions and computes my program, and it interacts with an on-chip memory called a cache, And what this cache is trying to do is speed up our program's execution by exploiting principles that computer architects rely on, like data locality, which says that as I compute on data, if I compute on data recently, I'll probably be computing upon it in the future. And what this is going to do is, in the common case, it's going to change our program's execution based on the program and the underlying data. So that is all well and good, but it has security implications. So let's take a simple example where, in addition to seeing the inputs and the outputs of this process, the attacker can also see some meta information, such as the amount of time that it takes to run the program. And let's put that in context with a particular victim program. So this is, of course, a toy program, but it illustrates some important concepts that carry over to important programs like cryptography. So what this program does is it takes a secret bit of input called S, and it makes two memory operations, one of which is going to unconditionally access address 0 in the program's address space, and then the second of which is going to access one of two locations in memory depending on the value of the secret. So T-table AES, which is a crypto function, looks exactly like this. And what we're going to do is we're going to analyze, depending on the value of S, the different ways that this program can execute from the view of the attacker, who can say view execution time. So what we do is we look at the two different values that S can take on, because S is a bit. So in the first case, when S is 0, we see that to execute the first instruction, because we have this cache here, we're going to have to go out to some lower level of memory and grab a data block and bring it into cache, because the cache was initially empty. And so we call this a cache miss, and it takes a long time. And then the second time we access memory, because S is 0 in this case, which means that the second load is going to go to the same address as the first load, we're going to be able to get the data from the cache, and that subsequent access, which we call a cache hit, is going to go faster. So from the purposes of this example, we call this execution miss, comma, hit, to mean that the program ran fast. Now we analyze the second case. What happens if S is equal to 1? Well, if S is equal to 1, the same thing happens on the first load. We have a slow cache miss. And then the second access is also a miss, because S is equal to 1. The second load is going to go to some different block in memory, and we're going to have to once again grab it out of main memory. And so in this case, we have a miss, comma, miss. The program runs slowly. And this is kind of the crux of the problem. We have two observable executions of the program, fast and slow, and which one occurs is directly determined by the value of S. So if an attacker can see this additional meta information, in this case execution time, it can use that to directly infer what the value of S was. Okay, so that's kind of a very simple example. It gets worse. For example, in modern deployments like cloud, we try to maximally utilize our shared hardware on the cloud, which usually means that it's not just that the attacker can see something coarse-grained like execution time. It can also potentially co-locate onto the same machine and learn more fine-grained information about how the cache is used. For example, it can deduce things like the precise program access pattern, the sequence of accesses that the victim program makes, as opposed to just the bulk aggregate of hits and misses. And the gimmick in the last two slides is that there was nothing special about cache in this example. The more general principle is that microarchitecture is continually used or not used depending on different secret dependencies in our victim programs, and we can get the exact same type of hardware resource usage changes in both time and space, not just through cache, but through any of the other mechanisms on our much more complicated processors. So, of course, any computer architect would know that the picture does not look like what I drew on the left-hand side in actuality. It looks like what is shown on the right, where we have cores, potentially multiple cores, where each core is made up of a complex data path, multiple levels of cache. There might be multiple sockets, all of which are sharing some last level cache or DRAM. There could be, and probably are, multiple levels of virtualization separating application software and bare metal. And speckled all throughout this picture are different hardware features, all of which can be measured to deduce secret information. For example, attacks have been demonstrated by monitoring contention on arithmetic unit ports, arithmetic unit timing, branch predictor state, 4K aliasing in the memory and the virtual memory subsystem, cache banking, both inclusive, non-inclusive LLCs, DRAM row buffers and DRAM port utilization, the RAND unit in the CPU uncore, and the list goes on. And even worse, what we've learned in the past several years is that there's not just attacks that are synchronous to specific instructions that are executing, but there's a much more dangerous class of attack called read gadgets. So what I mean by that is the following. If you look at our previous example, so this was the same unsafe program that we were looking at before, this program P. There is a sound mechanism for, at the software level, blocking leakage of the type that we see here by changing the program P. The idea is to do work that is kind of worst case independent of the secret value. So this is a rich field called constant time programming. And the idea is that instead of conditionally touching memory based on the value of S, you just touch both locations and then you take the value that you actually needed at the end. And this works, it incurs performance overhead, but it works if you can point your finger to a particular instruction and say, this instruction's execution is the source of the leakage. But not even this is sufficient to block these types of attacks these days. Since 2018-17, we're now living in a world where there's a conceptually far more dangerous type of attack, where instead of you being able to point to a synchronous point in the program where the attacker is getting the information from, there's a process through which an attacker, through cleverly orchestrating microarchitectural state, can construct what is, you can think of it as conceptually this function read, which we sometimes call read gadgets. So what a read gadget is it's this conceptual subroutine where the attacker controls the operand. I think that the operand, the window's in the way here. The operand is this little a here. And the execution of this subroutine, and this is again by coordinating microarchitectural state, gives as output the value of the program's memory at that location corresponding to the operand. And if this type of attack exists, it's devastating because it's no longer synchronous with the victim program's instructions. And furthermore, if the attacker can control the operand, which is kind of the signature of these read gadgets, it can just twiddle the operand over time and leak bit by bit the victim's entire program memory. So Spectre attacks, for example, are one type of attack that exploits speculative execution, which semantically give us read gadgets, but they're not the only one. Okay, so this talk, in response to all of this, is about principled low overhead defenses against microarchitectural attacks. I'll be focusing today on speculative execution attacks like Spectre, but I'll be kind of talking more broadly at the end of the talk. So I just want to, before I get into the technical details, I want to say something about what I mean by principled and low overhead and give kind of the starting point, simple insights which drive the rest of the talk. So just to kind of make my philosophy clear, when I say principled, what I mean is that on the previous slides, we saw that there were these little devil pictures all over the place. Many so-called points where I can leak information by modulating hardware resources. We call these side covert channels. So there's many of these. The attitude I'll be taking in this talk is that it's a fool's errand to try to block any one of them, because that's just going to result in a whack-a-mole game, and there's a 10 billion transistor chip that we have to deal with, and it'll be never ending, and I'll never be able to prove anything clean about my system. So the approach here is not going to be to focus on specific microarchitectural side or covert channels. It's instead going to be with respect to broadly all microarchitectural side and covert channels, which are just different hardware resources that live on the chip. I'm going to try to establish a higher level security property, which at the end of the day is going to give software designers a cleaner view of the world, where they don't have to think of the processor as that nasty white box that I had on the previous slide. They're going to be able to look at the processor like a black box and know for certain that particular secret values that they're interested in keeping private are going to flow through the black box as if there was no chance of leaking them over any channel. So try to simplify the world for the programmer. So that's principled. Motivation for low overhead, well, of course, we all care about low overhead. That's obvious. But one thing I will say is that I'm not going to compromise a clean security property to get performance optimization. So all the performance optimizations for the rest of the talk are going to be subject to maintaining a clean security property. Okay, so with that said, what's kind of the secret sauce, which kind of kicks all the ideas into high gear? Well, it comes down to a really simple idea that's been around since the dawn of time. So we see this manifest today, especially in the intelligence community. If you've ever heard of top secret versus not secret data, the basic principle is that if you have top secret clearance or are dealing with top secret data, you can't pass that top secret data to an unclassified context. So there's this rule which says that classified should never move to an unclassified context. So more recently in the 70s, the computer science community reappropriated this idea, and it kind of spun off what is now a very rich subfield in computer science called information flow. We kind of call classified and unclassified high versus low, but it's kind of the same type of idea. We don't want high to go to low. And what we're going to see in this talk is I'm going to once again reappropriate this idea in this setting, where I'm going to say that I don't want what we deem to be secret data, and how I define secret data is going to be more nuanced. I don't want it flowing to an unclassified context, which you might interpret to be, I do not want it flowing to one of these channels through which it's going to leak. And so that kind of gives us the intuition for the security side of things. I don't want classified going to unclassified. The low performance side of things is a little bit more nuanced, but the way to think about it is if you take the different combinations of classified and unclassified, the only restriction in information flow that I care about is classified to unclassified. If you have classified data and computing upon it, moving it around, keeps it in a classified context, that's still allowed. Likewise, if you have unclassified data, computing upon it, moving it around, it can move to a classified context or it can stay in an unclassified context. That's also perfectly fine. And kind of abstractly, what these rules mean when they become hardware mechanisms is whenever I see an X through an arrow, that's going to be a restriction. It's going to be telling the microarchitecture it can't be doing something, which is usually going to be causing performance overhead to maintain security. But whenever you don't see an X on an arrow, that means that the microarchitecture can just kind of go full steam ahead. And so we want there to be security subject to eliminating as many of the X's as possible so that we can get as much performance back. Okay, so that brings me to the outline of the technical part of the talk. And so the talk is going to be talking about 3 different recent papers that we did. The first on speculative taint tracking, the second on speculative data oblivious execution, and the third on kind of my parting thoughts, more broadly speaking, which is related to a paper we had out earlier this year. So speculative taint tracking is a comprehensive mechanism for defeating speculative execution attacks. Speculative data oblivious execution is a performance framework that we build on top of speculative taint tracking to get performance back. And then the last part is kind of a module off on its own. I'd just like to say that if the material in the talk is of interest to you, the work on speculative taint tracking, which kind of led to the subsequent work, originated through an earlier paper that we had in my group called Data Oblivious ISA Extensions, which has a more broad threat model. It protects more than just speculative execution attacks. So you can kind of think of speculative taint tracking as optimizing Data Oblivious ISA for speculative execution attacks. So if you're interested, you can kind of go back a little bit. And if you're still interested after reading about Data Oblivious ISA Extensions, I highly suggest you read both Glyphed, which came out of our community about 10 years ago by Tim Sherwood and his collaborators, Mohit Tiwari, and others. And also there's a very rich literature which has heavily influenced all of my work that spans theoretical cryptography all the way to high performance computing and applied crypto called, quote, data oblivious computing, which I've contributed to, but it's a much larger subfield. So I have a bunch of links at this URL here if you're interested in learning more. That's kind of influenced all the works. And then finally, if you want to go back to the fundamentals, there's the seminal work on information flow started by Denning back in the 70s. So just to kind of give a sense for what the landscape here is if you're interested in reading further. Okay, so without further ado, we're going to dive into the first technical part. This is going to be the bulk of the talk. The next 2 parts after this will be really short, just to kind of give the key ideas. This is going to be the really dense technical part, but I'll pause here if anyone has a question or two, and I'll try to intercept the questions on the chat bar if anyone has them. The crowd, oh no, that was an old comment. Okay, I think we're good. So let's keep on going, and if any questions come up, we'll just roll them over to the beginning of the next part. Okay, part 1 on speculative taint tracking. And again, the idea for this is to provide a comprehensive protection against these so-called speculative execution attacks. So let me start, let me make sure my keyboard works again, good. So let me start by just giving an example for what these attacks are. So people might know these attacks because they came up in the press recently as Spectre and Meltdown. So this was a big deal back in 2018. The idea with these attacks is that the attacker can exploit speculative execution on modern microarchitectures to leak more privacy than we originally thought possible through these microarchitectural side and covert channel attacks. So let me just give you kind of the classic example. There's many like it, but this is kind of the one that people typically see first. So we have a program on the left-hand side, or a snippet. So this is like a bounds check that you'd see in JavaScript or browser code. And what the attacker is going to do is it's going to exploit the fact that modern CPUs use prediction to maximize instruction level parallelism and performance. And so the hardware, the microarchitecture, unbeknownst to the program, is going to make a prediction as to this branch's direction. So this branch is saying, if the address is in bounds of an array, execute the code, otherwise don't. The hardware is going to make a prediction, regardless of whether this predicate is true or false. And it's based on that prediction going to execute this code. And the idea is that the attacker can train or just get lucky and see that the predictor guesses wrong. So if adder is actually greater than n, we're going to predict that this branch should be taken. And that's going to enable the attacker to execute this code that should have never been run. So what happens when adder is beyond the bounds of this array? Well, in the case of this particular example, because adder is just this free variable, depending on what possible values it can take on, it can read off this array if it's actually greater than n. So let's make a pessimistic assumption, which is the original assumption that the Spectre authors made, and assume that adder is actually controlled by the attacker. So now adder can be anything within the array or out of the array. It can be any value in memory. And what we're looking for, or what the attacker is looking for, is an instruction where we read memory at that address and load it into a register. So now the attacker has in its hands this red value spec val, which corresponds to any piece of program memory as dictated by adder. And then second, we call this an access instruction because it, quote, accesses disallowed or secret information. And then second, what the attacker is looking for is it's looking for a subsequent instruction which is going to form in that kind of synchronous way of thinking about things, a side or covert channel which is going to leak the operand value. So in this case, if there's a second load, going back to the hash example that we had before, which takes the spec val as its operand, then the attacker is going to be able to communicate that value of spec val based on how the load executes. And so we have access and transmit, kind of a two-step process. And then speculation ends, and this is usually where microarchitects throw up their hands and say there's no problem with speculative execution because execution squashes, only correct retired state gets actually retired, and none of this ever happened. But the point is that in this short period of time when the misspeculation is happening, this race condition, the attacker can get in and exfiltrate the data. And this is really bad. You can maybe see at this point how this forms a read gadget. If the attacker is able to control the value of adder, it can kind of steer adder around and leak the program's memory word by word. Okay, so that's kind of a basic lowdown on Spectre attacks. And so here's the key insight with STT. Very simple. It's sufficient for security if we can prevent secrets from reaching these so-called covert channels. In the case of the previous slide, this load, the second load. So kind of going back to our example to get a sense for why this is secure and why it gives us a lot of performance back, let's consider this kind of table here. So we're going to walk through the same example again. I added a line of code, this simple arithmetic, just to kind of illustrate a point. But we're going to walk through this code instruction by instruction, and we're going to be asking two questions. A, does the instruction at this line create a covert channel as a function of its operand? More precisely stated, does the execution of this instruction modulate hardware resources, microarchitectural resources in time or space as a function of the operand? And is the operand a secret? So let's just walk through the code. In the first line, well, at the very beginning, we have this misprediction. In the first line of code, we have a load. So it does create a covert channel, because whether a load goes to one address or another could mean a hit versus a miss. But the operand adder is not a secret. In fact, we said it was this attacker-controlled value. And because it's not a secret, we don't need to protect it, which is to say we don't need to do anything special about its execution to prevent information from leaking to the attacker. Great. Second line of code, we have this arithmetic. Let's just live in a world for a second where this plus operation is some simple single cycle ALU op where no matter what the operand value is, it just kind of goes through the ALU in a single cycle, which means that this add instruction does not create a covert channel. So it doesn't create a covert channel. Its input operand is a secret, but again, because it doesn't create a covert channel, we don't need to protect it. Great. And then the third case, this is the case that leaks the information in the original Spectre example. It leaks that information because A, that second load being a load does create a covert channel. And B, the input operand is now this spec val value, which is a function of the original return value of the first load, which means that we do want to treat it as secret, or at least we want to consider it specially because it was accessed under the shadow of a misspeculation, which may resolve to be incorrect. And so we do protect this instruction, but we don't protect the others. Now, furthermore, when speculation eventually resolves correctly, at the moment that the branch resolves, in the event that the branch resolved correctly, we now know that if it resolved correctly and we actually took the branch, that this value spec val was fine to read because it must have meant that adder was less than n. And so if we define what we mean by secret value as a value which is speculatively accessed, now that we know that that value is going to retire, we can say, okay, it's fine that that value is going to be communicated somehow because it's eventually going to reach retired register file state. So we can say for a moment, and I'll define this more precisely in a slide or two, that this operand is no longer a secret, which means that now one of these columns completely turns green and that protection is no longer required. Finally, if we squash execution, all we need to ensure is that protection was enabled up until the point of squash. If that's true, then at the moment that the squash happens, everything gets wiped away. And I forgot to say this before, there was a kind of critical sentence here. How do we implement protection? What I was assuming for this example is if we hit this case where we have a secret that reaches a covert channel, a sufficient protection, which we can prove to be correct later, is simply to delay the execution of that instruction. So I'm sorry for not mentioning that before. But the idea is delay until it becomes non-speculative and then allow to execute or squash. Okay, so that's it really. So that's speculative taint tracking. We have a secret, we need to prevent it from reaching a covert channel. It's exactly the same idea that I said before, which is we don't want classified data going to an unclassified context. So are we done? The answer is no. The reason being that it's all well and good to define a policy like secret does not go to covert channel. But if you're going to live in that world, you have to be really sure about what you want to call a secret, how to track those secrets, and what you exactly mean by a covert channel. Because, hey, I said on the previous slides, covert channels could be everywhere. So how do we tell what's a covert channel and what's not a covert channel? So that's going to be the rest of the STT. Actually, I'll come back to this in a second. That's going to be the rest of the STT part of the talk. We're going to be going deep on what is a covert channel. And to do that, we're going to create a model, a conceptual model for understanding the different types of covert channels that come about in microarchitecture. And the second part of part one of the talk is we're going to develop a new way of tracking information flows of speculatively accessed data, data that is speculatively accessed, but I'm not sure whether it's actually going to retire. So this is the rest of the talk. Now, because I just forgot the ordering of the slides for a second, let me just say something quickly about the security definition that we're after here. If we define what we mean by secret as speculatively accessed data, which is to say data that we don't know if it's going to retire or not, and it was brought into the register file by a speculative instruction. If that's what we define as a secret, and we allow protection to be disabled on state that eventually retires into the register file, then the security definition, the implication that we get from defining secret like that is we allow arbitrary speculative execution to only leak what eventually reaches retired register file state, given the non-speculative semantics of the program. So you imagine your program, the non-speculative architectural register file state of the program at every point in the program's dynamic execution. Whatever the retired register file is at that moment in time, we have no say over. We're going to let it leak. That's totally fine. But we're not going to allow to leak any data which is brought into the register file by a speculative instruction, like data returned by a load, to leak until we know that that data is eventually going to retire. And the reason why this kind of compromise, this is not the strongest security definition, but the reason why this security definition is interesting is that it means that while there might still be leakage from speculative execution, there will be no chance of getting a read gadget. Because what a read gadget does is it, based on the adversary's control of some value like adder, it's going to reach into program memory and try to leak that. We're going to protect all memory as it comes in from the cache subsystem. We're going to not allow it to leak until it is deemed bound to retire. And by that point, the speculation will have resolved and we'll have guaranteed to squash. Okay, so now let me just walk through the two kind of deep dives that we're going to do here. First on this model for understanding covert channels, and then second on tracking information as secrets flow through the pipeline. So this is really, if you've kind of missed pieces of what I've said so far, this is really the core, I think, intellectual meat of the entire talk and is arguably the most interesting part. So this is like 5 minutes, and if you miss everything else, I think that this part is kind of the coolest part. And so what we did in this project was we did a deep dive to try to understand the different types of ways that microarchitecture can be used to form covert channels. And we came up with this model. So this model is not perfect. We can view this at a lower level of abstraction, like at flip-flops and gates. But I think that this kind of hits a sweet spot between being sufficiently high level and giving intuition for when different bits of microarchitecture can be used to leak secrets. So here's the model. What we say is that covert channels are broken into two classes, so-called explicit channels and implicit channels. If you've ever read the information flow literature from the programming language community, explicit channel, implicit channel, this is synonymous with implicit and explicit flow. And furthermore, we did a deep dive that only came up because we're dealing with this at the microarchitecture level on the different types of implicit channels that happen because of microarchitecture. So I'll go through examples of what each of these are, but we broke this category of so-called implicit channels into ones that contain a so-called explicit branch or implicit branch. And we furthermore peeled out that both of these types of channels can leak both at prediction time and resolution time. And this is new to this work. Okay, so let's define each of these and walk through the model. So an explicit channel is going to be an instruction that has operand-dependent hardware resource usage in time or space as a function of its operand, or operand-dependent hardware resource usage. So an example of this is a load. A load instruction, depending on its address, is going to go this way or that way in the cache. It may hit or it may miss. But there's other examples as well. So for example, data-dependent arithmetic like floating point with subnormal micro-opposites will also have operand-dependent timing and would also form an explicit channel. Now, likewise, we have implicit channels, which are a bit more subtle. What an implicit channel is an instruction or a sequence of instructions that execute in different ways, again, take different hardware resource usage patterns based on a secret. So these instructions kind of team up, and how or that they execute depends on a secret value. So the simplest, most traditional example of this is a branch with a secret or data-dependent predicate. So if you have a branch whose secret is the predicate, then the fact that this load's address is not sensitive, so I'll use red to mean sensitive or private and green to mean public or non-sensitive. The fact that this load's address is non-sensitive is not important. What's important is that the load executes at all, which is a function of the secret. So you can also leak information that way. Okay, so now what I'm going to do is I'm going to do a deeper dive on the different types of implicit channels. So kind of like the classical example of implicit channel based on that description is branches and jumps, secret, predicate, and branch. Okay, so now we're going to do a deeper dive on these so-called implicit channels. So the first class of implicit channel is one that features a so-called explicit branch. So these are just control flow instructions like branches or jump instructions. Like that's why it's called explicit branch. Now, I'm going to go a bit deeper and explain how these instructions can leak at both prediction time and resolution time. So we're going to do prediction time leakage first. And I'm going to work through several examples here where, for the purposes of the examples, I'm going to say that secret values are red, non-secret values are green. And what we're looking for is, if I twiddle the value of a secret, will the memory access pattern induced by load instructions change? And if it does, we have a channel. If it doesn't, we don't have a channel. So in this, going back to this example with a secret branch predicate, if I go left on the branch, I see one access pattern. If I go right on the branch, I see another access pattern. That's kind of just the model we'll use to explain the examples. And we're concerned with all covert channels, not just ones that result from changes in memory access pattern, but just for these examples, we'll talk about memory access pattern. Okay, so explicit branches at prediction time. How do they leak? Here's the example. So suppose you have two branches, one with a secret predicate, and then some branch later on with a non-secret public predicate that has on each side of the branch a load to a different non-secret address. The question is, does the execution of this load leak information as a function of the secret? And the answer, because of branch predictor aliasing that we have in machines today, is yes. Counterintuitively, even though this younger branch has everything about it public and there's nothing about it private, the fact that this older branch executes with a secret predicate can have the potential to taint the predictor state as a function of the secret. And if branch predictor state aliases, it could be that the branch prediction for the second branch goes down in a direction that reflects on the secret, which means that we're going to see either one load go out first or another load or both loads depending on the number of squashes. So there is actually a secret dependence through the branch predictor that influences the memory access pattern. This is explicit branches at prediction time. Next, explicit branches at resolution time. When a branch resolves, do we leak? This example is subtle. So suppose you now have an if statement, an explicit branch, and you have a load with a public address, and this load is control and data independent of the branch. And the question is, once again, does the memory access pattern through the data cache unit change as a function of the secret value? And just to make things harder on ourselves, let's assume that the branch predictor state is not a function of sensitive information. So it's clearly not leakage at prediction time that we're talking about. It's something else. So you look at this, software person looks at this and says, no way, there's no dependence on the loads address for the secret predicate because it's control and data independent. There's nothing going on here. But if you're a microarchitect and you understand how the machine is implemented with speculative execution, there actually is a secret dependence here. Because if the branch predictor state is public, depending on whether that state agrees at branch resolution time with the value of the secret predicate, we're either going to get correct speculation or incorrect speculation, which means that in one case, we're going to get a pipeline squash, and in another case, we're not, which depends on the secret value. And depending on whether we see a pipeline squash and how far the misspeculation gets before we squash, we might see this load executed twice. So we'll go down the wrong path, we'll execute the load, we'll squash, we'll re-execute the load. So we either see the load execute once or twice. But once again, we have a secret dependent condition. I see 2 questions. I'll take them at the end of the section, but feel free to pile them up. Last in the model, we just talked about explicit branches. Now let's finish this off and talk about implicit branches. And they leak at the same points, prediction and resolution time. What's an implicit branch? Same question as before. I have a store to some secret address, this value foo, followed by a load to some public address into a register bar. Will the value of the secret influence the memory access pattern to the data cache unit? Again, the load address is public. Look at this, a software person looks at this and says, no, there's going to be no influence. But again, we as microarchitects know that there's a number of mechanisms which try to exploit aliasing in our load store data access pattern, which conceptually gives us a branch in the hardware that lives at the microarchitecture, but does not live at the software level. So for example, modern processors have store to load forwarding, memory dependent speculation, and other mechanisms that are going to have different implications on hardware resource usage, depending on things like, does the secret alias with the subsequent load address, which is public. So in the case of, say, store to load forwarding, if there's an alias between secret and the load address, you don't make a cache access, you just forward from the store queue, and otherwise you do make a cache access. So once again, we do see, depending on fine-grained pipeline conditions, secret dependent hardware resource usage changes. And this has an analogous leak at prediction time versus leak at resolution time. For example, if we're talking about memory dependent speculation, you might have something like a store set predictor, and all of a sudden you have the exact same principles being used with this implicit branch that we had before with the explicit branches. Okay, so that was the model. And we're going to use this model to develop a uniform protection strategy for the secrets that are flowing through the pipeline. I'm going to try to get through this part a little bit faster, glossing over some details and deferring them to the paper, but I'm going to try to get the high level bits. So we need one major ingredient before we can take that model and use it to mitigate these attacks. What we need is a way of tracking how speculatively accessed data flows through the pipeline. So kind of conceptually, the way this works is really simple. Whenever a speculatively accessed or a speculative instruction accesses some data that may eventually be squashed, like a load instruction, we're going to taint that data. So kind of in a word, we're going to taint all secrets. And we're going to flow that taint through data dependencies. If some instruction uses an operand, we'll flow the taint through. Kind of like a traditional taint tracking architecture, and there's been ones proposed outside the context of speculative execution attacks. So just kind of going to this example, we'll taint the return value of the load, we'll taint the value B, which is a dependent, and we'll be able to recognize that this value B is a function of the original load returned value. Now, importantly, and this is new to this work, we're also going to want to untaint as soon as possible. So I said we want to protect data as long as it's a function of speculatively accessed data. And then as soon as the speculation melts away, we're going to want to untaint. So typically, taint tracking schemes don't have this primitive called untaint. I'm just going to assume that we have it for free for the purposes of explaining ideas. And I'll say one slide about how we actually implement this untaint scheme in a single cycle with simple hardware. But we'll just assume that we have the ability to propagate taint and to untaint when speculation melts away for the moment. Okay. And just as a kind of side comment, data is tainted implies that data is speculative, but not the other way around. Okay, so now the last bit that we need before we're done is we need a way for the microarchitect to identify explicit channels. So we need to point to all the instructions that have operand dependent resource usage. And we also need the microarchitect to identify implicit channels, control flow instructions, load store pairs if we have store to load forwarding, things like that. Now, once we have these two things, taint tracking and the identification of these channels, life is a breeze, so to speak. So the way that we're going to block information leakage through all these channels is to apply an analogous mechanism to each one of them. So to block explicit channels, we're going to delay the execution of instructions creating those channels until their operands are untainted. Thumbs up. Next, to block prediction time implicit channels for both implicit and explicit branches, we're going to delay updating predictor state until the predicate of that explicit or implicit branch is untainted, which is kind of the same thing as saying delay execution in the first bullet. And then to prevent resolution time implicit channels, we'll delay resolution until the branch predicate is untainted. And that's it. Now, why is this great? It's great because it allows us to do a lot of work on speculative data without delaying anything. So we can execute all instructions with untainted operands, full steam ahead. We can execute any safe instruction that does not form an explicit channel, even if it has a tainted operand. We can, and this is really the key part, we can safely predict on both implicit and explicit branches, even if those branches have tainted predicates. And the only way that we're going to incur performance overhead is if our prediction is wrong, which means that our prediction resolved slower than it would have before because we're delaying resolution. So this is great because if prediction accuracy is high, which of course it should be, then we're going to incur no overhead from blocking these types of channels. So this is kind of, if you're a software person working on information flow, this is always the example that you bang your head against the wall over. If you have untainted data, but there was a transformation made on that data due to a secret dependent control flow condition, you typically just throw up your hands and say everything after the secret dependent branch is tainted. This is taint explosion in the classical setting. We don't have to worry about that because putting these properties together, what we get is that the program counter register on the machine is always and only going to be a function of non-speculatively accessed data. The predictors are never going to be a function of speculatively accessed data, and there's going to be no behavior in the pipeline that occurs and changes hardware resource usage as a function of tainted data. Okay, so we have 10 minutes. I can wrap this up in 10, but what I'm going to need to do is to skip a little bit. So what these slides talk about is how to quickly implement the untaint operation. So I said we need to kind of blink on and off this untaint kind of on a dime to be able to disable protection as quickly as possible to improve performance while not compromising security. So I'm not going to have time to go through the details. All I'm going to say about it is that the idea is we can couch this untaint operation as adding a new dependency on each instruction, which resolves when older speculation melts away, and using the existing instruction wake-up logic to broadcast when that dependency resolves. So we can kind of reformulate this problem as one which microprocessors support today in modern Tumasulu style pipelines. Okay, last thing I'm going to say on STT before I just say something about performance results is we have a companion security analysis to this paper if you're interested in reading about that, where we go through kind of the details about how we prove a novel non-interference property, which is kind of getting us the security and showing us why the scheme is secure. So I'll just point you to the paper for that. So performance, just kind of a very quick snapshot. We compared STT in 2 different settings, which count different types of speculation as being dangerous. That's the difference between the right and the left graph. Against a baseline where you just delay the execution of every load until all older speculation melts away. That's what delay execute is called. And kind of the upper, like the one bit of takeaway here is that delay execute's very slow. Speculative taint tracking, STT, is much faster. The performance overhead at the end of the day is kind of between 8 and 15%. So it's not negligible, but it's much better than doing the naive thing. Okay, so summary: high performance, provable security protection, no software changes, no memory subsystem changes, all changes restricted to the core pipeline. Okay, so that's really the main part of the talk, and I can very quickly get through the second part in a few minutes, just to kind of communicate the cool idea and then wrap up with a conclusion. But Mark, do you think I should look at the chat log now, or should I just push until the end of the hour?
I think we should you could look at the chat log now and answer some of the questions. I think for the people who are watching, you can be excused at the top of the hour if you have to go. Otherwise, we'll just continue a little late for people who are interested.
Okay, great. All right, so let me just go up a little bit. I think I got several.
You don't have to answer every question either. Just pick and choose.
Okay, maybe I'll just pick the top one because it appears in order, so I don't have to read them, and then we'll take the rest up to the last half hour. Does your definition of implicit explicit branches rely on the underlying ISA at all? Would conditional execution, like in ARM ISA, need to be handled differently? Explicit branches do depend on the ISA because they refer to control flow instructions. Conditional execution, the definition's evading my mind at the moment. Can you quickly remind me what it is, and then I can think about it for a second?
It's like with predicated execution, right? Where you have like if the predicate is 1, continue, otherwise convert it to a no-op. Like that style.
Okay, got it. So it depends on the implementation. And this maybe kind of half answers your question. If there's something in the semantics of the ISA, which I think would not be the case here, that the work needed to execute both sides, whether the predicate is true or false, has to happen regardless of the predicate value, then we would interpret that type of instruction as an explicit or as not an explicit branch because the work is being done regardless. So cmove, if you have a memory mode operand in x86 as an example, you have to do what that memory mode operand needs for you to do. For example, if it causes a TLB miss and becomes a page fault, you need to go through the work of doing that in the x86 ISA specification, which would be an ISA level indicator that that instruction is an explicit branch, even though the predicate might resolve in the other direction and you may not logically need to perform that memory read operation, but it would depend on the ISA spec. So sometimes not, and we can kind of maybe take the rest of the details offline. Okay, I'll have to push the rest of the questions until the end, which will be fine because the end is nigh. So what I'm going to do is I'm going to go through this next part quickly so that we can end kind of on time. And we have all the setup that we need to understand this part. So speculative data oblivious execution is a performance optimization framework that we can use on top of STT to improve STT's performance. There's a very simple idea, which is kind of the top level idea. And then I'll conclude by kind of giving my view of the future of processor security. Okay, so what's the idea here? So going back to STT, it's worth asking where the overhead in STT is coming from. So it's kind of like between 8 and 15%, and depending on who you are, this is a large number or a small number, but let's just imagine for a second that it's a large number. Where is this overhead coming from? So there's 3 different reasons why STT incurs performance overhead. We delay the execution of instructions that form explicit channels, for example, loads. More generally, we call these instructions transmitters. So like loads, floating point instructions, there potentially are different types of transmitters. So we just kind of call them transmitters collectively. And then the next 2 mechanisms are these implicit channel handling mechanisms, delaying branch predictor updates and delaying branch resolution. So it may not come as a surprise to a microarchitect, but if you look at this scheme, what you end up getting is most of the overhead comes from the first protection mechanism, delaying the execution of speculative load instructions with tainted operands is the bulk of the overhead, over 90%. And because our predictors are very good, the overhead of delaying predictor updates and resolution is relatively small. So kind of the fundamental problem that we need to solve to speed up STT, and it turns out other speculative execution defenses as well, they all kind of get stuck on this point, which is that you have to delay the execution of instructions that create explicit channels. That's kind of the core problem. So the question is, how do you get around that? And so the idea is the following. So I've been using this word data oblivious. I pointed to this literature in the background part of the talk. So the idea here is that we can actually safely execute these so-called transmit instructions like loads early, even if they have secret operands or sensitive operands, which is great because it gives us high performance. If, and this is a big if, we execute all variants of those instructions from a hardware resource usage standpoint. And this is a big if because it creates a huge potential performance overhead. So this is kind of similar to saying, you're going to execute a load with a tainted operand, execute all possible ways that that load could have executed. So execute different loads that hit in all the levels of the cache, miss in all the levels of the cache. So you think about this idea and you're like, okay, this is a completely terrible idea because there's way too many ways that an instruction can execute that would cover the different microarchitectural resource usage patterns. And so the key idea to get the performance back is to add new predictors, dynamic or static, that predict what type of hardware resource usage this instruction is going to need, regardless of what its operand is eventually going to need. So this is like saying, don't execute all ways a load could execute, or evaluate a load in all possible ways. Evaluate one type of load, a type of load that goes to a particular set in the cache, to a particular cache, and unconditionally returns data from that particular part of that particular cache, and return that instead. And if we can just somehow make this predictor high accuracy, then we're once again in a world of delight. We can execute these instructions early. Their hardware resource usage is now a function of the predictor and not their operand. And if the predictor is good, then we get most of the performance benefit back. And the whole reason why this works, there's all sorts of ways why if we constructed this idea on top of a vanilla microarchitecture, this idea would be leaking out of the predictions, it would be leaking out of the resolutions, because as we just went over in the STT slides, predictions and resolutions leak. But if we build it on top of STT, then we're able to do it safely. So I have in the next few slides just kind of a working example, but it says the same words again. So take floating point, for example. Floating point can be fast or slow, depending on whether the inputs are subnormal. And so making it data oblivious is akin to executing both fast and slow variants of the floating point, waiting until the slower of the two finishes, and then taking the result that you actually needed. And the whole idea with this speculative data oblivious execution is designing a predictor which predicts whether you'll need fast floating point or slow floating point. And voila, that's beautiful, because most of the time floating point operands are not going to be subnormal. So you can just design some simple predictor and virtually the overhead of executing transmit instructions that are floating point melts away. So the reason why all of that works, it comes down to this primitive, and I'm skipping these slides just to kind of get to the upshot here. It comes down to perhaps the kind of most important takeaway from the STT work, which is that if you combine the STT mechanisms together, delaying resource usage, variant instructions as a function of their operand, delaying predictor state updates, delaying predictor resolution, if you put all those things together, we now have a methodology for making predictors safe. And so we've kind of turned this problem around on itself, where the root of speculative execution attacks was bad predictors. Now what we're going to do is we're going to add predictors to the system that we did not have before to lower the overhead of mitigations against these attacks. That's kind of like the one takeaway that I'd like to leave people with for this part of the talk, and this slide basically says the same thing. And we get better performance than vanilla STT. Okay. All right, so now we're at the end. We have about 3 to 4 minutes left, if people can hang around. So I just want to kind of end the talk by kind of thinking broader and saying something about where I think processor security is going to be going next. And this is just my view. And I also want to talk about some new read gadgets, which I think are pretty cool. So the way I want to start this is by saying that microarchitectural attacks, these side covert channel attacks, kind of our view of them prior to 2018 is kind of like one bubble, where we kind of viewed them as traditional, quote unquote, traditional side channels. And by traditional, what I mean is that I can kind of point my finger to a particular instruction and say that on your average microarchitecture, this instruction is going to leak privacy. So like a branch predicate, if that's secret information, that's going to leak. If I have a load instruction that has a secret address, that's going to leak. So that was kind of the world prior to 2018. Now, in 2018, Spectre and Meltdown happened, and so the worldview changed. And so if you go to kind of a researcher in this area, they'll say that the world now looks like this kind of Venn diagram, where each of Spectre and Meltdown, and we kind of like jointly call them speculative execution attacks, they're both kind of distinctive from the traditional attacks, but all three of these kind of share some common DNA, namely that we're exfiltrating data through microarchitecture, which is either used or not used as a function of secrets. And so this is kind of what people said the world looked like in 2018. What I'm going to argue, just based on my experience in this field for the past 2 years, is that actually the world doesn't quite look like this from an academic computer architect's perspective in terms of, do I understand the root problem? You can argue that Meltdown is a smaller problem. I can write down the security property that we need to enforce on a napkin that would solve Meltdown. So Meltdown is arguably easier to think about. And Spectre, and this is more nuanced, there's a lot of leakage that you can get through Spectre, which actually was already leaked with non-speculative execution. So there's leakage that Spectre really adds to the game, like this notion of leaking all program memory. But a lot of what you could leak with Spectre, you could have already leaked with the original attacks, which is kind of a non-obvious insight that has kind of occurred to us through the past 2 years. So you can argue that there's more overlap between Spectre and traditional attacks. So this is really kind of what the world, I think, should actually look like as of 2018. But actually, this is itself missing the big picture. Namely that, and this talk today is absolutely partly to blame for this. We've been chasing speculative execution for the last several years when really we have processors being at this point 10 billion plus transistors, and speculative execution makes up a very small number of those transistors. And so we have to start looking broader and asking, what and how does other microarchitecture leak privacy on processors today? And just to kind of give 2 examples for why this is an important problem, there's been kind of a drip of papers since 2018, which have introduced completely different microarchitectural mechanisms. Rambleed, which exploits a property similar to Rowhammer in the DRAM, Safecracker, which we did in a conference this year, which talks about leakage through compressed caches, which likewise show that given different victim programs, you can likewise leak all of program memory similar to Spectre. And these have nothing to do with speculative execution. And I would have said something to give intuition about how the compressed cache attacks work, but I'll just kind of use this as an advertisement to go read the paper. It appeared in AskWAS this year. And we can build read gadgets out of it, but I'll also defer those to the paper. What I want to end with, just as the concluding slide, is I solemnly believe that it's computer architects that need to be thinking broader. So I think it's very easy for computer architects to say, okay, the security community is going to go out there and they're going to find these attacks in microarchitecture. But that's just not the way to be thinking about it. For example, a recent quote from a security colleague was, microarchitecture attacks are akin to dissecting a frog, where the difference between normal dissection and this dissection is that this frog actually was engineered by intelligent design. And that's how the security community views this problem. They have to stumble around in the dark as if they're dissecting some creature that we don't fundamentally understand, because they don't have the background that a computer architect has. Whereas if we computer architects start putting our heads together and thinking about these problems, we can, no pun intended, leapfrog over this hurdle of trying to understand the frog and get to the root problems a lot faster than I think any other community would be able to. So I'm going to just use that to end the talk, and now I can start going through questions. And if anyone has questions that are not on the chat, feel free to just say them verbally and we can just kind of walk through them.
Okay, so this is Mark again. While Chris is starting to look at the chat, let me just say, since we're past time, you're allowed to leave. But since there's no disruptions, you're allowed to stay, and I think we'll just keep recording. Remember, anything you put on the chat, your question, will be recorded. And Chris has graciously agreed to stay till 1:30, so we'll stay that long, but you don't have to. So hopefully that gives Chris a little bit of time to look at some of his questions.
Okay, let me just quickly...
Keep recording, Mark.
Let me quickly skim through these and see if I can kind of organize them. Okay, all right. I think I can go top to bottom here, and as we discover redundancy, we can just deal with that redundancy on the fly. Okay, First question by David, slide 4 of STT. So am I gonna be able to, yay, the chat window did not disappear on me. Slide 4 of STT. Oh, okay, I'll go back to it so that people can see what the question was about, but I know what you're talking about. I think that this slide is sufficient to illustrate the point. Okay, can you elaborate why is using an ALU not a covert channel? Does it become a covert channel when linked with explicit branches where now hardware contention available ALUs is dependent on the secret's value? Yes. So in this example, because the add, and I hope I said this when I went over the slide, that I'm just going to live in a simple world where this add operation is a single cycle ALU op, where regardless of the operand's value, we're going to just execute it in a single cycle. That means, and there's some details here that I'm skirting off to the side because there are front-end optimizations that a processor can perform, which would create hardware resource usage changes as a function of an operand. I'm assuming kind of like a simplistic pipeline here. That means that this instructions execution is not going to form a covert channel. So like, I think the way to intuit this is think a pipeline diagram or a waterfall diagram that we all learn in computer architecture classes. The question to ask in terms of whether this instruction is going to form a covert channel is, if I take the operands of the instruction and I quantify over them, is the waterfall diagram going to evolve in a different way? And if we're talking about something like a 5-stage pipeline with a single cycle ALU unit, the answer is no. This add instruction goes through and that's kind of the end of it. To the second part of your question, if there's a branch before the add, is that going to create a covert channel? Yes, that's going to create an implicit channel with, if it's a branch instruction, an explicit branch. And that's an important point. So at some point there was an attack after Spectre came out called Spectre, where the attacker was utilizing the power on characteristics of floating point units as a way of transmitting information. And what microarchitects that I'd spoken to were saying we needed to do was block that signature of power on to fix the attack. And that was not the way to think about it at all. The attacker was not exploiting this power on mechanism. They were simply exploiting the fact that it was happening. And so that's the same principle that's going on here. So if you execute an add instruction in the shadow of a branch, it causes an implicit channel. The root cause of that implicit channel is the branch instruction. And if that does not answer your question, feel free to just speak up and we can preempt or speculate down different paths as we answer subsequent questions. And this will also be related to a question that Mark asked in a few questions, which I'll get to in a second. Okay, Ravi's question. Do you think that a principled solution for all or a larger set of security leaks, i.e. beyond only speculation, would render STT moot, or do you envision that they blend? More holistic solutions do exist. So I'm not going to claim that this is the only one, but if you're interested in this, reading the Data Oblivious ISA paper is a good start. So the idea, that was that paper that I said kind of motivated or inspired the STT work. So what that paper does is generalize the same style of protection where you disallow secrets from traveling to covert channels, where we define secrets more broadly. We don't say that a secret is just some piece of speculatively accessed data. We now think that, or call a secret any data that a user declares as secret, and we kind of trace that secret through the program's entire execution. So that blocks both speculative and non-speculative covert channels. And the mechanism in the Data Oblivious ISA paper solves speculative execution attacks as a special case without introducing new rules. But the performance overhead is significantly larger and it forces you to adopt a different programming model. And that's usually the Achilles heel of more comprehensive protections. To kind of see why the problem is significantly more difficult in the general case, think about it this way. There's going to be programs that, regardless of what microarchitecture you run them on, are going to leak privacy. For example, if you have a program like while secret loop forever, there's nothing that a microarchitecture level defense is going to be able to do to block leakage of that program. It's like, it's a similar type of attack, but you can clearly point the blame to the software. And we haven't fully grokked the difference between those that I can point to and blame the software on and those that I can point to and blame the hardware on, because usually both hardware and software interact in interesting ways and they both contribute leakage. But kind of the upshot of that example is that the only way to make that example secure is to run the program forever. So your performance overhead is infinity. So I think we need to do a lot more in this kind of area to handle the programs that are interesting in a way that is not deplorable overhead-wise. Okay. Mark's question, is your covert channel taxonomy complete, cannot miss any covert channels? And the very related and important follow-up question, how does an architect identify all covert channels and guarantee that none are missed? Okay. This is a very good question. Taking the words of a very wise person I listened to recently, no model is perfect. All models have limitations. And the model that I spoke about is no exception. In particular, if you kind of twist your head a certain way, the taxonomy that I laid out between explicit and implicit channels collapses on itself, and you can all of a sudden formulate any explicit channel as an implicit channel, because I can write out any instruction as a big case statement. So there's at some level a lie that is going on in this classification. I think that this model is useful because it handles many cases that are relevant to microarchitects, ranging from what we consider to be the traditional covert channels to the much more subtle covert channels like memory-dependent speculation, store-to-load forwarding, and other optimizations that I can formulate as branches in hardware. And actually, maybe a better way to think about implicit channels and to more directly answer your question is, yes, implicit channels by themselves cover every possible microarchitectural covert channel, but they're kind of an else statement in the sense that I can formulate any of these as a giant case statement. And so I think the question, they're complete, but the question is whether this level of abstraction is right. And I'll argue that the level of abstraction is good. It covers interesting cases in, I think, an intuitive way. But I'm not going to claim that it's perfect, for the reasons I said before. And but it's not the end of the world, which is to say, going to your second question, how can an architect identify all of these channels? So that's a real problem. At the end of the day, a microarchitect, we can kind of gauge how good the abstraction is by handing a microarchitect a blob of RTL and asking them to point out all the explicit and implicit channels. I don't think that's the way to go long term. I think that the model is good for the short term to help us understand how microarchitecture leaks. But I think that long-term, we need automated tools for identifying these various covert channels. And STT does not have a lower level of abstraction for identifying covert channels. It just has this notion of explicit and implicit. But if you're interested in that, there's a lower level abstraction in the Data Oblivious ISA paper. It's actually in a footnote, sadly. This footnote it might be the biggest contribution of the whole paper. It's a footnote in the Data Oblivious ISA paper that talks about a way of modeling an arbitrary microarchitectural side or covert channel as a generalization of what we teach in computer architecture classes, namely waterfall diagrams or pipeline diagrams. So if you think about every flip-flop in the processor as being a box in your waterfall diagram and watching whether each box is, quote, used versus not used by a program in each clock cycle, we can use that projection of a program's execution on a microarchitecture, and by twiddling secret bits, if that projection changes, then that indicates that there could be a microarchitectural side or covert channel. So actually, the topics, there was a topics version of the Data Oblivious ISA paper, and I tried to spend a lot more time talking about this in simpler language than the Data Oblivious ISA paper did. But that would be just one way of that's like one step closer to having an automated tool discover these, that I think is what we need to do long term. And the STT model kind of grew out of that as a way of trying to make that more reasonable to a normal person. Okay, next question. Ravi, does STT increase leaks across other side channels? For example, would the tainting, untainting delays due to classified versus unclassified boundaries leak other information which makes the processor vulnerable to other attacks? The answer is no, but let me qualify very carefully what I mean by that. So all STT says is, suppose you have a program's execution, and I just consider that program's dynamic execution as a trace of what all the flip-flop state is in each processor clock cycle. Now, if you look at that trace more abstractly, you can point to particular flip-flops that were a function of data read by speculative instructions that eventually got squashed. So you can just kind of go through the trace and point to them. And all STT guarantees is that all of data that falls under that category, data that is accessed speculatively that eventually gets squashed, will not influence hardware resource usage at the flip-flop granularity in either time or space. So another way of saying that is that if you point to any of that data, so-called transient data, which eventually squashes, that the pipeline diagram is not going to change as a result of what different values that speculatively or transiently accessed data takes on. So that's literally what STT gives you. Now, to your question, do you create other side channels? I think to the specific example that you gave, the answer is still no, because of exactly that guarantee that I just stated, but let me rephrase it in a way that I think is a lot more useful. If you put together STT's mechanisms, delay predictor state updates, delay resolution, delay the execution of instructions that cause explicit channels, you get a very cool property. So this property, I think, was first mentioned explicitly in the Glyph paper as being a really cool property to have if you can somehow get it. And that property is, if your mechanism can guarantee that the program counter register, which is responsible for determining the next instruction to fetch, if your mechanism can guarantee that the contents of that register are not a function at any point of secret data, however you define secret, so in this case, speculatively accessed, then the clouds part, manna falls from the heavens, and your life is significantly better. And so STT gives you that property because of these three mechanisms in concert: delayed state updates for predictors, delayed resolution. And what that means is that at any point in the program's execution, you can, without any knowledge of speculatively accessed data, faithfully draw out the waterfall diagram of that program's execution starting from that point on. And you'll know, again, blindfolding yourself without looking at any of the speculatively accessed data, exactly when every squash is going to happen, when every resolution is going to happen, and all of those events, getting to your question, like when do resolutions occur, et cetera, all of those events are completely separate from secrets. It's kind of the most subtle thing to understand about STT. I think maybe a good way of thinking about it is, imagine you have a reorder buffer that you never resolve branches for, and you just unroll that reorder buffer. If you do that, you can see how the contents of the reorder buffer are clearly not a function of resolution. And then if, in addition to that, you have the property that the predictor is also a function of not secret data, which we get by delaying updates to the predictor state, that you've effectively turned the program into straight line code. That's what you get, which is very nice. Okay, next question. Oops, I went to the top. Ravi. Oh, Ravi, I think Ravi's question I just answered. Joshua's question. Doesn't SDO introduce the potential for leaking information, albeit a small amount, now that the prediction delay is dependent on SDO's predictor accuracy? And if so, how do you quantify how much is leaked versus the performance benefit? Aha, the answer is no. It leaks no additional information. In the following sense, SDO, all it's doing is adding predictors to the processor. And what STT tells us is that how predictors predict and when those predictions get resolved are going to be completely independent of speculatively accessed data. And so maybe the way to think about it is that in STT, the predictors that we already had, like the store set predictor, the branch predictor, whatever kind of the predictors that the microarchitecture already had, are leaking zero data, or at least are behaving in a way which is independent of speculatively accessed data. Likewise, the idea in SDO is, okay, well now we can just add predictors, and assuming we pipe them into the same framework that we applied to the original predictors that were already there, we'll get the same security property. So zero additional leakage. And I think that's it for the questions. So feel free, if anyone else has a question, to please feel free to ask.
Okay, I think this is probably just a good time for us to thank Chris. Since it doesn't work for everybody to unmute, I will give you the solo applause.
Thanks so much for having me. This was a lot of fun. It's great to be giving a talk again, despite everything that's been going on. So thanks so much for having me.
So, subtle stuff, and I love how computer science is all about doing meta stuff. So having a predictor predicting what the predictor is going to predict, what we like to do. All right, bye everybody.
Wonderful. Thank